How's it going, everyone? In this video, I am going to explain the concept of what's commonly called Hill force. Okay, so this is the force that causes a mass to slide down a slant. Okay, where does that force come from and what it's equal to, and why is it equal what it's equal to? So if you have a mass on a slant, and let's say the angle of that slant is theta, well, what forces do you have acting on that mass? Well, you have the force of gravity, F subscript g, and that's pointing straight down. And you also have the normal force, F subscript n, which is 90 degrees from the surface of the ramp. Now, why that normal force is there is because when you place a mass on a surface, that mass will actually deform that surface, right? Because it presses down on that surface as a result of the force of gravity. Now, that surface, because of its natural structure, wants to return to its original shape, right? Imagine you place something on a pillow. What happens when you take it off of the pillow? Well, the pillow or the cushion starts to return to its original shape. Well, that happens with hard surfaces too, but that indentation might be microscopic, so you don't see it, but it is there. And that's why the object doesn't fall through, because of that normal force. So that's why it's perpendicular to the surface. Now, these two forces add up. And when we add forces, we place them tip to end. So this downward arrow is the direction and magnitude of your force of gravity, right? And your normal force, by the way, is this magnitude and direction of that diagonal arrow here. So when these add up, you end up with a force that moves down along the slant, and that is the Hill force, right? That's the force that'll push the object down the slant. Now, what is that Hill force equal to? And to figure that out, we're actually going to look at this triangle here and use some trigonometry. So let's scroll down and redraw this. Okay, so there is our slant, okay, or our slope with angle theta, and we're going to imagine our mass is right here at the top, right, and there is our normal force, okay, which is perpendicular, and there is our force of gravity, which is straight down, okay. Now, notice that you have, well, this is a right angle here, right? So this is a vertical line right here, and this is a vertical line. So right here you actually have a Z pattern, all right? Which means that this angle here, let's call it alpha, is equal to this angle here, let's also call it alpha, because they're equal to one another, which means these are similar triangles. And if they're similar triangles, right, so because we have our 90-degree angle and theta and alpha, and on the top smaller triangle we have our 90-degree angle and alpha, which means that this top angle here must also be angle theta. And recall that the Hill force ends up being this side of the triangle right there. Okay, so through some trigonometric properties, we can find exactly what Hill force is, the sine, and what the normal force is, right? So the sine of theta is going to be the Hill force, that's the opposite side of a right angle triangle, divided by the hypotenuse, which is our force of gravity. As for the cosine of theta, well, that's the adjacent side to theta, right? So that's the normal force, again divided by the hypotenuse, which is our force of gravity. Now we can put in what these are actually equal to, right? So our Hill force divided by force of gravity, well, the force of gravity is the mass of the object multiplied by gravitational acceleration. And we can put that in the bottom equation here. So rearranging these equations, we can get what normal force and Hill force are in terms of the angle of the slant, or the angle theta, and cosine and sine, right? And what we get is that the Hill force is equal to mg sine theta, and the normal force is equal to mg times the cosine of theta. So that is how we get Hill force, what it's equal to, what normal force is equal to as well, and where that normal force comes from. And what's interesting when you think of these equations is what happens in the extremes. Imagine theta is equal to 0. Well, that means you have no slope as well. You have no slope at all, right? Well, sine theta is going to be 0, right? And cos theta is going to be equal to 1, okay? Now, what does that imply? Well, it implies that our Hill force is equal to 0. Now, that makes sense because if you have no angle of inclination, your mass is not going to slide anywhere. As for the cosine of theta being equal to 1, well, your normal force is just equal to mg, which is equal to your force of gravity. And that's exactly what happens if your mass is on a flat surface. Your normal force cancels out your force of gravity and your mass just stays still. Now, what happens if theta is equal to 90 degrees? Well, then sine theta is equal to 1 and cos theta is equal to 0. Okay, so what does that tell you about Hill force and normal force? Well, your Hill force is going to equal mg. Now, think about that. If your angle of inclination is 90 degrees, well, there's your slope and there's your mass. Okay, your mass isn't sitting on the slope. It's just going to fall, right? The force with which your mass is going to move down along your slope is just the force of gravity, because the slope isn't underneath your mass at all. And what about normal force? Well, if cosine of theta is 0, well, then your normal force is also equal to 0. Well, there is no normal force, right? Your mass is not pressing up against the surface, and so the surface isn't trying to reclaim its natural shape by pushing your mass outward, right? There is no normal force. So that is how that works. So I hope you enjoyed that, and until next time.